Günaydın arkadaşlar. Birazdan başlayacağız. Okay. All right, let's start now. Let me recall what we did last time. Well, last time we were talking about higher order homogeneous differential equations. So let us recall this. Well, we had something like this. An equation, nth order equation with constant coefficients. Okay, a and y is equal to 0. It's an homogeneous equation. Here, the coefficients are constant. AIs are constant. Well, we convert this into linear system, and from this linear system, we get a characteristic equation. So let's write the characteristic equation. Well, that was basically P of lambda is equal to lambda to the n plus a1 lambda to the n minus 1. Basically, it's like in the equation, differential equation, you replace y by lambda, and here the orders of the derivatives will be the power in the polynomial. And it goes like that. An is equal to 0, okay? Well, what we do is we find the roots of this equation. If the roots are distinct, then the solution is easy to write down. If this is the case, the first case, case 1, let's say. P alpha has distinct roots. Say, for instance, lambda 1, lambda n. In that case, the general solution is, we discussed this last time, when we have distinct roots, the general solution is basically y of t is equal to, well, it's the combination of e to the lambda I t's, c1 lambda e to the lambda 1 t plus c2 e to the lambda 2 t, and so on. Okay, so this is the easy case. When we have distinct roots, we have this form for the general solution. Now we will discuss today when what happens when we have repeated roots. Okay, when we have repeated roots, the general solution will be in different form. Let's discuss this. Any question so far? All right, let's continue with repeated roots. Well, in the case of distinct roots, when you have complex roots, you do the similar thing. The only difference is you take the real and imaginary parts of the solution, complex solution. It's even easier when we have complex root because you work with only half of the roots. You don't need to take the conjugates, right? Because one complex solution gives you two real solutions. So once you find the roots, the rest is easy. Well, today we will talk about repeated roots. So suppose for now we have one repeated root, and general case will follow from this. First, suppose that we have a repeated root, lambda 0 is the only root of P alpha, P lambda. This is the characteristic equation, characteristic polynomial with multiplicity. And that means it repeats n times. Or more explicit, we can write P lambda as lambda minus lambda 0 to the n. Okay, so that means it repeats n times. Multiplicity means it repeats n times, okay, like this. So suppose this is our repeated case. We have characteristic equation in this form. In that case, we will write the fundamental matrix for the solution. So we need Jordan form, right? What is the Jordan form in this case? Then the Jordan form Jordan block, let's say, because we have only one eigenvalue, Jordan block is this. It's this matrix. On the diagonal, we will have lambda 0. Otherwise, well, let's write this. And just about the diagonal, we have ones. Okay, otherwise everywhere we have 0. Okay, like that. So this is the Jordan block corresponding to this lambda 0. Okay. Well, what is the exponential matrix? We will write the fundamental matrix. So we need exponential of this e to the jt. Well, maybe let's compute this here. E to the jt. Remember, exponential of this is e to the lambda 0t times, well, larger. We had this matrix 1 t squared over 2, and it goes like that, and t to the n minus 1 over n minus 1 factorial. Okay. A little bit here. 1 factorial. Oops. Okay. And you continue this, and 0, 1, t, and so on. 0, 0, 1, t, and so on. And well, basically we have 0, 0, and somewhere here on the diagonal we will have 1, and this is 0. So, okay, like that. So remember this form for the exponential of Jordan form. Well, this tells you what? This tells you basically the fundamental matrix the fundamental. Well, maybe let's also write here P as well. Remember, P consists of eigenvectors, and P is, these are eigenvectors and generalized eigenvectors, right? The columns are, the first one, for instance, it's an eigenvector. The rest are here generalized eigenvectors, right? These are column vectors, and we have P, and well, the fundamental matrix, which gives the solution, right? It's basically, let's call it psi. Psi t is P times e to the jt, right? That was the fundamental matrix. And the columns of the fundamental matrix will give you here the general solution, right? Any combinations of the columns will give you the general solution. So what are the columns here? Well, you take here, we take this P and multiply with e to the j here. So this row and this column will give you, maybe let's write here. We have e to the lambda 0t times v, right? E to the lambda 0t times v1. This is the first column, okay? For the next column, we take here this column. So it's going to be e to the lambda 0 t times v1. It's like this, by the way. Maybe let's use parentheses. t times v1 plus v2. Like that, okay? And next, you go like this, okay? So you continue this. And the final one will be like e to the take this to left. The final column will be the following. It's going to be longer. E to the lambda 0 t parentheses, we have t to the n minus 1 over n minus 1 factorial v1 so you take this column and this row here and multiply this two, okay, dot product, and we get plus other combinations, right? It's like we have at the end vn here. So this is the resulting fundamental matrix. So we have columns, and remember, the first entries of the columns will give you the solution of the original nth order differential equation. Değil mi? Yani bunlarda bir sürü kalım var. Bu kalımların ilk entry'leri n'inci dereceden denklemin çözümlerini verecek. Ama ilk entry'lerine bakarsanız, so when we check the first entries of each column, in the first column we have e to the lambda 0 t times a constant, right? The first component of v1, it's a constant. The second one, we have t times e to the lambda 0 t times another constant. Next one, it's going to be t squared times blah blah, okay? So this tells you basically e to the lambda 0 t times, or maybe let's write here like this. This tells you the solutions of nth order ODE, remember, at the beginning. Maybe let's give a name for that. Let's call it star here. This one. Well, that was the case of distinct roots. Maybe let's. Well, in that case, maybe let's write the equation. What is the equation in this case? It's it's not easy to write down. Okay, let's skip that. But we understand what it is, right? There is an ODE here corresponding to this characteristic equation, and the solution of nth order ODE corresponding to p lambda is there are many solutions, so they are the linear combinations. They are the linear combinations of the first entries of each column. So they are the linear combinations of such functions, e to the lambda 0 t t times e to the lambda 0 t, t squared times e to the lambda 0 t, and you go up to t to the last one here is t to the n minus 1, okay? So t to the n minus 1 times e to the lambda 0 t, okay? All right, so we write all the solutions. Well, we have, these are independent, linearly independent. Okay, you can easily check this, linearly independent. Which means basically general solution is going to be the combination of these solutions. General solution. Y of t is C1 e to the lambda 0 t plus C2 t times e to the lambda 0 t, and you go like that, okay? Cn t to the n minus 1. Maybe let's remove this parentheses. We use this for derivative usually. E to the lambda 0 t, okay? So let's put this in a box because we have now nice formula for the general solution when we have the repeated root. All right, any question with this? Well, this is the theory, of course. In practice, it's going to be much simpler. Let's do some examples. Well, if you have more repeated roots, you do the same thing and take the combination. Let's do some examples. So let's solve this IVP, initial value problem. Y double prime minus 2y prime plus y is equal to 0. Okay, what are the initial values? Initial values are y0 is equal to 1 and y prime 0 is equal to minus 1. Okay. All right, let's solve this. So let us write the characteristic equation for this. It's basically p lambda is equal to lambda square minus 2 lambda plus 1. And this is nothing but lambda minus 1 square, right? Is equal to 0. This tells you 1 is a repeated eigenvalue. It repeats twice. Multiplicity is 2 here, okay? So lambda is equal to 1 is repeated eigenvalue. Or repeated root. Well, in that case, maybe let's say repeated root because we don't have a matrix here. Yeah, well, it follows from the matrix representation, but since we don't write the matrix, maybe it's better to write like it's a repeated root. Well, what we just talked about here, the general solution is going to be like this. The general solution y of t is equal to C1 e to the t plus, then you multiply this bit with t, C2 t e to the t. Okay, this is the general solution, right? When we have repeated root, we have e to the t and t times e to the t, and the combinations of this too. Well, so what are C1 and C2? This is an initial value problem, so you need a unique solution. Here, y0 is equal to 1. Y0 is what? It's C1, right? Because the second term will vanish. T times e to the t will be 0 at 0. And e to the 0 is 1, so we get this. It's equal to 1. So we get that C1 is equal to 1. Y prime 0. What is y prime t? Y prime t is you take the derivative of y, it's going to be C1. Can we see this easier? No. Okay, let's take the derivative of y. C1 e to the t plus okay, C2 e to the t plus, we use the product rule here. Okay, we take the derivative of y from here. And we get what? We get y prime 0 is C1 plus C2, right? Which is equal to minus 1. This is given in the question, but C1 is 1 already, right here, which implies C2 is equal to minus 2. So let's plug this back into the general solution, which implies y of t is e to the t minus 2t e to the t. This is the solution of the equation, differential equation, okay? Any question with this example? Var mı soru arkadaşlar bununla ilgili? Well, let's see what happens when we have a repeated complex root. It's going to be similar. Let's do an example. Okay, let's consider this example now. Solve this equation, 6y second derivative plus 9y is equal to 0. Well, again, we write the characteristic equation. The characteristic equation is lambda to 4 plus 6 lambda square plus 9 is equal to 0. Or maybe let's write like this. What is this? This is basically lambda square plus 3 square, right? The square of lambda square plus 3 will give you this. So we don't have any real root, but we have complex roots. We have 4 complex roots. This is a degree 4 equation. We have 4 complex roots. Some may be repeated. Here, for instance, well, let's continue this. This is equal to lambda plus 3i lambda minus 3i, right? This gives you lambda square plus 3, right? And you have the square here, so we get square here, square here. So you see that here, 3i and minus 3i, these are repeated roots. lambda 1 is equal to 3i, lambda 2 is equal to minus 3i, are repeated roots. Well, it's enough to work with one of those, okay? Because when we take lambda is equal to 3i, since it is repeated, we have two complex solutions. Two complex solutions will give you 4 real solutions, and 4 real solutions will be enough because there's a degree 4 equation. So let's work with one of those. It doesn't make any difference. So let's take this one, okay? It's enough to work with this. It's enough to work with one of those. Okay. Since it is repeated, we will have 2 complex roots. So what are the roots here? What are the solutions here? The complex solutions, they are e to the lambda 1t, which is 3i t, and the other one is t times e to the 3i t, right? We have 2 complex solutions. Since we have repeated root, we multiply this by t as in the previous example. Now let us write the real solutions. Well, what is this? This is basically e to the 3i t is cosine well, I did some mistake here, sorry. It's not 3, but it's root 3. This should be root 3, right? Okay, so everything here is root in root minus root 3i, and this is root 3i, root 3i. Okay. Well, it's gonna be, remember, this is e to the I times some real number, root 3t. You can, maybe let's write it like this, it's better. Well, it's the same thing, but when we write like this, it's going to be easier to work with. Root 3t times I, okay? Continue like this. Similar for the other one. So this is going to be cosine root 3t plus I times sine root 3t, right? This is the definition of e to the I theta. And we have similar thing here. You multiply this by t now, t times cosine. This is the real part, root 3t, plus I times t times sine root 3t. Well, the real and imaginary parts are the solutions. So we have 4 solutions here. This one here, this one here, this one here, and finally that one here. Well, let's take the combinations. So the general solution. The general solution is y of, we have y, right? Y of t is c1 times cosine root 3t plus c2 sine root 3t and the rest are similar, but we multiply by t plus c3 times t times cosine root 3t, and finally plus c4 t sine root 3t. Okay. Any question with this solution? Var mı soru arkadaşlar bu çözümle ilgili?
Hocam şu son general solution'ı yazdığınız yeri bir daha söyler misiniz? Ya nasıl yaptınız?
Kompleks solution'ları yazdık. Kompleks çözümlerin reel ve imaginary kısımları da reel çözümler oluyor. Reel kısmı, mesela bunun reel kısmı burası. Imaginary kısmı da burası, değil mi? Benzer şekilde bunun reel kısmı burası, bunun imaginary kısmı burası. Bunların kombinasyonunu aldık. Aşağıya yazdık. Bunu yazarken de şunu kullandık. Belki şurada bir hatırlatayım. E üzeri i teta. Teta burada reel bir sayı. Bu şuydu. Kosinüs teta artı i sinüs teta, değil mi? Bu formülü kullandık.
Tamam. Teşekkürler, sağ olun.
Hocam,
Any other question?
General Solution'da C2 ile C4'te i yazmamız gerekmiyor mu?
Gerekmiyor çünkü bunlar reel çözümler arkadaşlar.
Tamam.
Yani çok bir önemi de yok aslında. Yani i aslında bir sabit, değil mi? İ bir sabit, dolayısıyla C3, C4'ün içinde var. Öyle düşünebilirsiniz. Yani C3, C4 olarak orada kompleks sayı da alabilirsiniz. O zaman zaten i'yi oraya atmış oluyorsunuz. Peki başka? Any other question? Peki. All right. Well, so what remains here is now we need to consider non-homogeneous equations, and there are many ways to deal with non-homogeneous equations. This is 4.3 in the book. It's method of undeterminate coefficients. Undetermined coefficients. So we will deal with non-homogeneous equations. Okay, non-homogeneous. That means on the right-hand side of the equation, we will have a function other than 0. Okay, so the purpose is, so here the goal is we want to solve non-homogeneous higher order linear ODE with constant coefficients. Okay. Let's take such an equation. Well, let's say we have y nth derivative of y plus a1 y n minus first derivative, and a n y is equal to, earlier we have this equal to 0. Now we will have this equal to some other function, b of t. It's a function of the variable t. Here, all the coefficients are real. They are constant. Okay. And bt is a function. Well, there is not an easy way to find a solution here. Okay. There is not an easy method to find the solutions in the general case. So what we can do is, in the simple case, when b is in the form of some well-known functions, we guess the solution. So let us assume here that this here non-homogeneous term b of t is a combination of some well-known functions. Okay, assume that b of t is a linear combination of something like something like t to the k e to the lambda t to the, here k is an integer, positive integer, e to the at times cosine bt, t to the k e to the at times sine bt. Well, in that case, if b is like this, then we try to solve this equation. Let's call it star here. Okay, to solve star, first we solve homogeneous equation. So find the general solution. Let's call it y h. H is for homogeneous. Solution of the homogeneous equation. Homogeneous equation is the same equation when b is 0. So you take let's copy this. Okay, this equation when b is equal to 0. Okay, this is easy to solve it because of the previous methods, right? So we look at the characteristic equation. If we have distinct roots, it's easy. If we have repeated roots, again, it's easy. You multiply by t, the repeated roots, t squared, and so on. And we write the general solution in that case. But the difficult part is to deal with the non-homogeneous part. So we try to guess a particular solution. Second, guess the form of a solution, let's call it y sub p. P is for particular, okay? Of a particular solution, let's say, of star as a linear combinations of functions from B of t. So this part is tricky, okay? How do you guess such a solution? We will go over this in the examples, okay? It's not difficult, but it's not trivial, I will say. So you will try to guess a particular solution as a combination of functions from the non-homogeneous part B of t. Then the general solution is the sum of homogeneous solution and the particular solution. The general solution is y of t. It's basically yh of t plus the particular solution yp of t. Okay, so this is the form of the general solution. We will follow this here steps to get the general solution. Let's do a simple example, then we will give a break. Y double prime minus y is equal to 2 times e to the 3t. It's a second order non-homogeneous constant coefficient linear ODE. Here, this is my B of t, okay? And the homogeneous equation is, let's start with the homogeneous part. Homogeneous equation. This is equal to 0. And the characteristic equation for this is lambda square minus 1 is equal to 0, which implies lambda is equal to plus minus 1. So the solution for the homogeneous equation, yht, is e to the t and e to the minus t. So you take the combinations, right? Plus c2, this. Now we move to the non-homogeneous part, the particular solution. We will guess a particular solution here. Look at the non-homogeneous part, e to the 3t. So you will guess your particular solution, the natural guess here. It's going to be in the form of e to the 3t. So yp t is going to be some constant, let's say a times e to the 3t. And we will find this a, okay? So a is a real number here. And what is this a, right? So what is it? To find a here, the coefficient, we will plug this into, since it's the solution of the, let's call it here star, it's the solution of the star, we will plug into star and find a. To find a, plug yp into star. And we get what? Yp double prime minus yp. It's what? What is yp double prime? You differentiate yp twice. It's going to be 9, right? 9 times 9a e to the 3t minus a e to the 3typ is equal to what? It's equal to e 2 times e to the 3t. Well, this tells you simply, here this is 8a e to the 3t. So a is equal to 1 over 4, right? A is equal to 1 over 4, which tells you that the general solution y is equal to yh plus yp, which is c1 e to the t plus c2 e to the minus t. What's the particular solution? A times e to the 3t. A is 1 over 4. 1 over 4 times e to the 3t. Okay, that's it. Any question with this example? Açık mı arkadaşlar? Var mı sorunuz?
Ya benim sanırım şeyle ilgili bir sorun vardı. Bu homojen kısımla ilgili.
Hı hı.
Yani böyle e üzeri 3 hani constant'la e üzeri 3t bunun solution'ı ya.
Hı hı.
Sanki böyle homogeneous kısım sağlamayacak gibi geliyor. Hani
Homogeneous kısmı zaten homogeneous kısmı çözmemesi lazım. Yani şey gibi düşün. Hani homogeneous kısma koyuyorsun, işte sağ tarafı verecek. Yani işte türev alıyorsun, kendisini çıkarıyorsun. Sağ taraftakine benzer bir şey olması lazım. Ne diyor mesela bu denklem? İkinci türevini al, fonksiyonun, ondan kendisini çıkart. Ondan sonra e üzeri 3t'yi elde et. O zaman bu e üzeri 3t çarpı bir şey olması lazım ki hani türev aldığın zaman, değil mi? Exponential'da türev aldığın zaman çok bir şey değişmiyor ya.
evet.
Yani homogeneous kısmı çözmüyor particular solution. Particular solution tüm denklemi çözüyor. Onun bir tane çözümü ama. Biz genel çözümü istiyoruz. Hani particular solution toplamda şunu çözüyor. Homogeneous kısmı çözmüyor, tamam mı?
Ama C1 e üzeri t artı C2 e üzeri eksi t hani
O homogeneous kısım. O sıfır, yani o sıfır durumunu çözüyor şunu.
evet o da sıfır durumunu çözüyor. Ha yani o zaman o mesela ben biraz daha düşüneyim.
Tamam. Şimdi
Aynen.
ne oluyor? Şimdi bir homogeneous kısım var, bir de particular solution var. O zaman sen bunu komple alıp denkleme koyduğun zaman burası zaten sıfır verecek. Burası da sağ tarafı verecek. Dolayısıyla denklemi çözmüş olacak. Sen düşün bakalım.
Biraz da. Tamam hocam. Teşekkürler.
Tamam. Let's give a break here for 10 minutes. So let's continue at 9:45. All right, welcome back. Any question, comment so far? Let's do another example. So let's consider now this maybe let's open a new page. So take this equation, y double prime plus 3y prime plus 2y is equal to cosine t. Well, again, this is a non-homogeneous equation. Let's solve the homogeneous part first, as usual. So homogeneous part equation. It's y double prime plus 3y prime plus 2y is equal to 0. And the characteristic equation is lambda square plus 3 lambda plus 2 is equal to 0, which implies, maybe let's write like this. This is lambda plus 2 times lambda plus 1 is equal to 0, which says lambda is equal to minus 2 and minus 1. We have two distinct roots. So the general solution for the homogeneous equation, okay, homogeneous equation, YHT, is C1 e to the minus 2t plus C2 e to the minus t. Let's find a particular solution. Particular solution. For the particular solution, remember, we look at the non-homogeneous part, which is this cosine t. Okay, so when we have cosine t, how do you obtain cosine t when you take the derivatives here, like second derivative, first derivative? Well, natural guess is this, right? Let's say y particular t is equal to a times cosine t, for instance. But the problem with this is when you try this, you will not get a particular solution. You can try this yourself, put into the equation here, this one, okay, star, and you will end up with no solution. The reason is when you take the derivative of cosine, here, for instance, you take the derivative of cosine, you will get sine function, right, minus sine. But there is no sign on the right-hand side. That means you never get an equation, equality, okay? So that's why instead of cosine here only, we will, do you have any guess? Well, derivative of sine is cosine, what?
B times sine t.
B times sine t, good. B times sine t is a good guess, great. Because when you take the derivative of sine, we will get cosine and you will get the right-hand side. So this is a better choice, right? And let's try this one. So we will plug this into star and plug in star. And let's see what we get. What's the equation? Second derivative and first derivative. Let's find first the maybe before we plug in, let's find the derivatives first. Okay, so what is yp prime? It's minus a sine t plus b times cosine t. This is the derivative of first derivative, and the second derivative is minus a cosine t minus b sine t. Let's plug into star now. The second derivative, okay, minus a sine t plus b cosine t. Second derivative plus 3 times. Well, sorry, this is the first derivative, sorry. Minus a cosine b sine. Plus 3 times the first derivative, right? Here, y prime, which is, oops, it's minus. Okay. Plus 3 times first derivative, okay. Minus a sine t plus b cosine t is plus 2y, okay, plus 2y to a cosine t plus b sine t is equal to cosine t, right? Right hand side is cosine t here, so it's equal to cosine t. So let's see what we get from this. What is the coefficient of cosine t from left hand side here? We have cosine t parentheses, we have what? Minus a plus 3b, right? This one here, plus 2a, right? Okay, so it's basically a plus 3b. Let's continue with sine t. The coefficient of sine t is minus b minus 3a, okay, plus 2b is equal to cosine t. So that means a plus 3b is equal to 1, and the coefficient of sine, which is b minus 3a, is equal to 0, because we don't have any sine function. There's sine here, so it's sine 3t, sine t. We don't have any sine on the right hand side, so we have 0 for the coefficient of sine t. All right, from this we can get a and b. Multiply the first one with 3, for instance, and add to the second one, you will get 9, 10. B is equal to 3, right? So B is equal to 3 over 10, and A is equal to 1 minus 3B, 1 over 10. All right, so now we can write the general solution. So the general solution YH, maybe let's write like this, Y of t is equal to the homogeneous part plus the particular part. Well, the homogeneous part was C1 e to the minus 2t plus C2 e to the minus t plus now the particular solution is a times cosine t. A is 1 over 10 cosine t plus b times, which is 3 over 10 sine t. Okay, that's it. Any question with this solution? Açık mı arkadaşlar? Var mı sorunuz?
Hocam benim bir tane sorum vardı.
Tabii.
Şeyde mesela bu konunun başında undeterminate coefficient'ın başında şey demiştiniz. Assume that BT'ye hani T üzeri K, E üzeri AT, kosinüs
Evet,
BT.
doğru.
Onları yaparken bu sefer E üzeri AT'ye hani böyle A'yı o zaman 0 kabul ettik. T üzeri K'daki K'yı da 0
Aynen,
yaptık.
aynen. Evet.
Tamam.
Yani o daha da genel formu. Onda da mesela şey kullanacaksın o zaman. Mesela diyelim burada kosinüs t yok da işte e üzeri at çarpı kosinüs t var. İşte o zaman yine e üzeri at çarpı kosinüs t, e üzeri at çarpı sinüs t gibi fonksiyonları kullanıp partikülası. O daha da tabii uzayacak o şeyi, çözümü. Ama bu da evet, bu o formda onun basit formu. Dediğin gibi oradaki a'yı b'yi 0 alıyor.
Tamam hocam. Teşekkür ederim.
Let's do another example. Oops. So let us solve now y double prime minus y is equal to e to the t. Well, it looks like a simple equation, but there is a trick here. We will talk about this now. Now the homogeneous equation is again y double prime minus y is equal to 0. The characteristic equation is going to be lambda square minus 1 is equal to 0. So lambda is equal to plus minus 1, which implies the homogeneous solution is C1 e to the t plus C2 e to the minus t. Okay. Let us find the particular solution. For particular solution, you may try a times e to the t, right? Try yp is equal to a times e to the t. But the problem is e to the t is already the solution of homogeneous part. So when you plug this into star here, what you get is plug into star. The second derivative minus itself, it's going to be the 0, right? It's going to be 0. A e to the t second derivative minus a e to the t is good. This is not surprising because e to the t is the solution of the homogeneous equation. It's equal to 0. Is equal to e to the t. So no solution for a, right? No solution for a. We don't get any constant a from this. So So that means the particular solution cannot be this. It cannot be in this form. In that case, the trick is, so that's not a good, okay. That's not a good choice. What we could do is, we could choose instead, take yp. Again, it's going to be like e to the t, but in order to obtain e to the t with second derivative and the first derivative, we will write something like this: a times t times e to the t. Okay, so this will help. So we will multiply e to the t with t, and then take the second derivative and subtract itself, and you will get something like e to the t, and we will find from this, we will find a. Okay. So let's see what we get. Y p prime now is going to be a times e to the t plus t times e to the t. Take another derivative, yp double prime. It's going to be e to the t plus, well, again, e to the t plus t times e to the t. Or simply you can write this as a times 2e to the t plus t e to the t. Now let's plug this into the equation. Plug and start. And we get what? A times 2e to the t plus t e to the t. This is y double prime minus y minus a t e to the t is equal to e to the t. Well, the nice thing is now, this is nothing but, we have a cancellation, right? 2a e to the t is equal to e to the t, which implies a is equal to 1/2 will give the particular solution. So the general solution again, y is equal to yh plus yp. Yh was c1 e to the t plus c2 e to the minus t plus the particular solution. It's 1/2 t e to the t. Okay. So basically what we did here is we guessed the particular solution in this form, because in this case, e to the t is already the solution of the homogeneous part. So there is no way to get particular solution in this form, a times e to the t. That's why we multiply by t, and we try with this, and we get the particular solution in that case. Any question? Var mı soru bununla ilgili? Peki. Tabii şimdi bu çok düzgün işleyen bir sistem değil. Çünkü niye? İşte sadece belli formda ise sağ taraf bunu uygulayabiliyoruz, değil mi? Well, what I'm saying is this method doesn't work always, because we apply this method when the right-hand side of the equation is in certain form, and this is very limited. And we will need a better method to solve non-homogeneous equations. So for this purpose, we will talk about annihilators. So let's talk about this. Annihilators. This is used solve non-homogeneous equations as well. Well, let's define some operators here. Definition. We will denote the derivative by capital D. So let's say D is the derivative with respect to t. Okay, so instead of d dt, we will say d for short. And by d to the j, we mean derivative of order j, okay, dj. Then this derivative operator is called differential operator, d to the k plus a1 d to the k minus 1 plus goes like this, a k is called a differential operator. Okay. Well, why do we do this? Because we want to write the differential equation in a simple form using this differential operator. Okay. So for instance, let's write this as a remark. This equation, remember we are dealing with this nth order differential equation like this. A and y is equal to b of t. This can be written as the following. We have differential operator now, so it's going to be like you apply so nth derivative here. That means you apply d to the n. That means the nth derivative. You apply d to the n to y, and then you apply n minus first derivative times a1. So a1 d to the n minus 1, and you go like this. Finally, you apply an. You multiply with an basically. So you apply this differential operator to y, and you get right hand side. Okay. So this is another way to write down a differential equation with differential operator. Okay. Is it clear? Any question with this?
Hocam D tam olarak neydi ya? Bir daha şey yapabilir misiniz?
Türev anlamına geliyor. D türev oluyor.
Bütün equation'ın türevi mi?
Neye uyguluyorsan evet. Yani burada mesela D üzeri mesela dy dediğin zaman maybe let me clarify this. Dy means dy dt, okay?
Anladım.
Or d square y means d square y dt square, okay? Açık mı şimdi?
Evet evet hocam. Tamam.
All right. Now let's define annihilator definition. So take a differential operator. So let LD. Well, this is like a polynomial of D. It's like D to the n, D to the n minus 1. It looks like a polynomial, so we will call it L of D. It's D to the K plus C1 D to the K minus 1 plus CK. Let's say this is a differential operator. Be a differential operator. Then it's called annihilator of a function B. LD is called annihilator of B of t, another function B of t, okay? If what? One, you apply LD to B of t, okay? And when you apply LD to B of t, you will get 0. Second condition, here the order here, K, is the smallest. K is the smallest integer. So that LD satisfies the first property. Number 1, okay? The definition looks complicated, but it's not. I will explain with some examples, don't worry, okay? Let's do some examples and try to understand what's an annihilator. Example. Let's take, for instance, take B of t is equal to t squared. What is an annihilator of t squared? That means you apply a differential operator to t squared and you will get 0. If you differentiate t squared by 1, if you differentiate once, you will get 2t. Twice, you will get 2. The third derivative will be 0. So that means, basically, if you differentiate this 3 times, you will get 0. And 3 is the smallest such order, right? Because 2 is not enough. If you differentiate twice, you don't get 0, you get 2. So this tells you basically d cube is the annihilator of t squared. Well, in general, you can guess this. What is the annihilator of t to the some power, let's say m? the annihilator of t to the m is, what's your guess?
M+1.
M plus 1. Here m is, I should say m is a positive integer. Okay. Here it's positive integer. D to the m plus 1, right? Because if you differentiate m plus 1 times, you will get 0, and this is the smallest such thing. So it's the annihilator. Well, this is an operator, differential operator, and we will call this LD, okay? It's like f of d, p of t, it's L of t, okay? And similar here, this is L of t, okay? We denote differential operators by L of d. This part is not very important, okay? L of t, okay, anyway. Well, let's do more examples. What about this? Let's say the function is e to the lambda t. Do we have an annihilator of this, or what is the annihilator of this? Well, if you differentiate this, d of e to the lambda t, what is the derivative of e to the lambda t? Lambda times e to the lambda t. By differentiating, you don't get 0, but what you can do is, if you apply d minus lambda to e to the lambda t, when you apply d, you will get lambda times e to the t. So you subtract lambda times e to the t, and you will get 0. That means here, this is an annihilator of e to the lambda t, okay? Which implies d minus LD, which is d minus lambda, is the annihilator of e to the lambda t. Okay, is it clear?
Hocam yani hani D böyle türev anlamına geliyordu ya.
Evet.
Hani D'den böyle lambdayı çıkarmak.
O da şu anlama geliyor. D ile türevi uyguluyorsun, lambda ile de çarpıyorsun sadece. Sonra da çıkarıyorsun.
Tamam hocam.
Yani şu demek bu. Bunu uyguluyorsun, bunu da çarpıyorsun, sonra aradaki farkları sonuçları çıkarıyorsun. O demek.
Tamam hocam.
Açık mı?
Yani hala böyle D'den lambdayı çıkarmak biraz böyle çok değil ama yani şimdi açıkladınız. Yani
Tamam.
önce türevini alıp lambdayla çarpıp
Evet, çünkü yani
eksi.
burada aslında diferansiyel operatörün tanımında var o biraz. Hani diferansiyel operatörde mesela ikinci türevi birinci türevi toplamak demek aslında iki tane fonksiyonu topluyorsun gibi düşün. Yani bir türev alma fonksiyonu var. Birinci türev alma fonksiyonu, ikinci türev alma fonksiyonu. Bunları topluyorsun demek. İşte türev aldıktan sonra topluyorsun ya da işte bu mesela şuradaki AK dediğin şey sadece o sayıyla çarpma oluyor. Yani AK mesela burada lambdaya denk geliyor. Şurada. Peki. Biraz daha örnek yapalım. Another example. Let's say BT is t times e to the lambda t. Well, again, you can try, well, e to the lambda t, the annihilator of e to the lambda t is d minus lambda. You can try d minus lambda for this one as well. When you apply d minus lambda, it's going to be, let's try d minus lambda to bt, t times e to the lambda t. You will get, you first apply this, okay, derivative. It's going to be e to the lambda t plus lambda times t times e to the lambda t. This is the derivative of the function minus lambda times, so you apply this now, lambda times this, lambda times t times e to the lambda t. Okay. Let's see what we get. We have a cancellation. This is nice. Cancellation. And what remains here? E to the lambda t. This is a good news because we get rid of t here. We don't have any more t, right? T times, we reduce this from t times e to the lambda t to e to the lambda t. So we get rid of this t here. But it's not zero. So what you do is you apply d minus lambda again. And when we apply d minus lambda to this one, we know that it's zero because d minus lambda is an annihilator of right-hand side. So this implies when you apply d minus lambda, that means d minus lambda, you apply this, so it's d minus lambda square t e to the lambda t is equal to d minus lambda e to the lambda t, but this is zero as in the previous example. And this tells you basically d minus lambda square, which is L of t, let's say, is the annihilator of t times e to the lambda t. Okay. Well, so what happens here when you multiply by t e to the lambda t, you have the square. You can generalize this and write the following similarly. Annihilator of t to the k is here positive integer, t to the k times e to the lambda t is d minus lambda to k plus 1. Okay. Clear? Any question? Okay, let's do a couple more examples. What about this? B of t is cosine a times t. What is the annihilator of this? Well, let's try. So we take the derivative, d of this is minus, well, derivative of cosine is minus sine, and you multiply with the derivative of inside, so minus a sine at. And let's differentiate this again because we don't get 0 here. So d square cosine at. You differentiate this again, so it's going to be, what is the derivative of this? You will get another a minus a square cosine at, which implies d square plus a square cosine at is equal to 0, right? That means d square plus a square is the annihilator of cosine at. Which is d square plus a square is the annihilator of cosine at. And similarly, d square plus a square, the same operator, is the annihilator of sine at. You can check this yourself. Sine at. Check this yourself, okay? Well, the question is, do we always have an annihilator? The answer is no. Can you give me such an example? Can you give me a function which has no annihilator? Var mı öyle bir fonksiyon, annihilator olmayan? Not all functions have annihilators. For example,
Ln x olabilir mi hocam?
güzel, ln x olabilir, güzel. Ln x olabilir. B of t, let's say ln t, good. Because its derivative is what? D ln t is 1 over t, not 0. And if you differentiate this, d square ln t is minus 1 over t square. And you can continue with this, and d cube ln t, for instance, 2 over t cube, right? And you never get 0, and you don't get 0 from any combination because this function 1 over t, 1 over t squared, 1 over t cube, they are linearly independent. So this implies ln t has no annihilator. Okay. Okay, maybe let's stop here. So next time we will continue with few examples, with few more examples with annihilator. And using annihilator, we will solve higher order non-homogeneous equations. All right, see you next week. Stay safe, bye.
İyi günler hocam.
Görüşürüz.
İyi günler hocam.